Now we're going to talk about system architecture, which in my view, in the sense of software for modeling and simulation, this is probably the most important module in the entire course, because system architecture is the bedrock, it's the keys to the castle. You've been hearing me say that this is what we can't outsource. We've got to have skills in system architecture in the government if we're going to build good systems that are cost effective and that meet our objectives. So we're going to start in this module here with a fairly high level overview of all things system architecture, and then we're going to follow with a couple of others that are just some specific points of view in how we might achieve that. First thing to keep in mind, absolutely first thing, is that architecture is not product. You are not architecting if you buy a suite of products. You can easily solve a problem by going and buying a Microsoft suite or an Oracle solution or what have you. Those companies are happy to supply you with a complete soup to nuts set of products to solve your problems. But that's not an architecture, or at least at the minimum, it is an architecture, but you're basically buying their architecture. Now that still may be appropriate in a case where something doesn't have a long timeline, you need something quick, you're going to be retiring it fairly quickly, maybe perfectly fine to go buy a product, don't worry about the architecture. But if you're talking about a program, this is a program we're going to run for multiple years and we want to be able to sustain it, you'd better be doing some architecting, and that's not buying a set of products. Architecture is about how the components work together to achieve some goal. And what we normally see with architecture is bubble charts with blocks, and there's a function in a piece of software and it kind of does this function, and there's another piece of block over here and it kind of does this function, and then there's a line between them, and that line will represent a protocol, it'll represent a file format or a data standard or something like that. So think of it this way, it's about the plumbing, it's not about the fixtures at the end of the pipes. It's about how the pipes make everything fit together. So I already hinted at this with outsourcing, but we need to outsource or accomplish our mission. The government is not built to do everything ourselves. We're not supposed to do that, even if we could. But we never should outsource our core competency. And architecture, in my view, is our core competency. It's far too important to yield to a contractor. It doesn't mean you can't have contractors, smart contractors, helping you with architecture. I'm not saying that. What I'm saying is that the architecture has to be owned by the government. We've got to participate. We have to take ownership of it. And that means we have to develop a workforce that's highly skilled in system architecture. And that's why we have the programs that we have now. So we're going to talk a little bit about how you deal with big software. Architecture isn't all that important, really, if you're talking about some little toy thing you're going to build. It really becomes important when you got big, expensive stuff with maybe tens of thousands or hundreds of thousands of lines of code. We're going to talk about modular architectures. We're going to talk about the role of open source, but if you recall from our open source module, that's not the solution. In fact, you can get some of the same problems with open source that you'd have with proprietary software if you don't think about architecture. Very importantly, we're going to talk about legacy systems and how to deal with them. Talk about what a legacy system actually is. Sometimes they're the skeleton in the closet that you really don't want to talk about, but you got to live with it. So legacy systems are existing computer systems which continue to be used because they still have a user pool, they still have a use, but very often they're systems that you'd sure like to put to bed. Within the government today, don't kid yourself, we still have systems that are running on old mainframes. We have systems that run on hardware that hasn't been maintained in years, that is new parts, etc., for the simple reason that we can't afford to rewrite the software to get off of that thing. So whether it's a VAX or something like that, these things are still around today. And you might say, well, that's stupid, just pull the plug and get off that thing. Easier said than done. Lots of software on those things, and getting the funds to rewrite something that already exists is very hard to do in the government. Nobody wants to pay for something that already exists, even if you make a compelling case for it doesn't have a lifespan behind it. We've seen as much as 75% of operating budgets going into maintaining legacy systems. So can you imagine being a program officer and you get your 100% budget for that year and 75% is gone before you can even do anything. Now with the other 25%, now you get to do something new. So try and get off the legacy system that's eating 75% of your budget by using only 25% of your budget. We talk about system architecture as the structure of components, their interrelationships, very important, and the principles and guidelines governing their design and evolution over time. Very important. This is non-trivial. Some of the things to look at when you're thinking about legacy systems, if you happen to have the misfortune of getting dropped into an organization where you've got to manage a legacy system, is typically very high maintenance costs. If there weren't high maintenance costs, you probably would have pulled the plug and gotten off of it anyway. So they're legacy systems because they have high maintenance costs and we can't get off of them. They have complex structure. They have obsolete support software. Sometimes the companies are gone. People don't even have the skill sets. We have systems that have programming languages that people don't even learn those languages anymore. You've got obsolete hardware that you can't replace. Definitely lack of technical expertise. There are companies out there that specialize in obsolete stuff because they know there's still a market in it for support, and they can be paid top dollar for something that you don't even want. They tend to be business critical. If they weren't critical, you'd have pulled the plug again. So you got to have it. It's your payroll system. It's your inventory system. It's something important. You end up with a backlog of change requests. People want things that are new and they can't get them. They're poorly documented. They're embedded with business knowledge. We'll talk about that in a minute, and they're typically very poorly understood because the people who built them are probably long since retired. And the reasons you'll get for why you're not going to get a nickel for changing it is, it works okay. Why should we change it? The cost is too high. It's a large, monolithic, complex thing. The cost is too high, so just keep it going. Retraining on a new system would be costly and lost time and money, so we're not going to do that. The system requires near constant availability. I don't have an opportunity to even pull the plug. I have to have a complete 100% solution sitting next to it before I can pull the plug from the old one and go to the new one. How am I going to do that? I don't have time or money for that. The way the system works is not well understood, so I'm not going to muck with it. And the user expects the system can be easily replaced when this becomes necessary, which is often a fallacy. So when we talk about state-of-the-art, DoD has a lot of legacy systems. If you don't think NMCI is already a legacy system, you're kidding yourself, because it is one. How in the world are we going to get off of NMCI if we decide that we want to go in a different direction for the key backbone infrastructure for the Navy and the Marine Corps? GCCS, GEECS, is another one that could be regarded as a legacy system. M&S has them. MTWAS can be viewed as a legacy system. Combat 21, JSAF. There's a lot of SGI hardware. SGI has been out of business for years. Their hardware is still out there being used in some cases because we can't get off of it. We talk about how, remember when we talked about JSIDs and the requirement to be joint, Commander-in-Chief says, well, everything should be considered for joint use. Well, is that really happening? Are we really doing it? Or are we still making excuses to not do that? I think the jury's still out on that. But these are still some of the problems that we're dealing with. There's something called a legacy system maturity model that I just want to show you because you've got these different generations where first generation is what we call mainframe. Everything, it's monolithic. Everything is wound into one system. The second is a stovepipe PC, which is very similar to a mainframe. It just runs on a smaller computer. The third is client-server, where we were splitting. The client was sort of a lighter weight front end, and a lot of the heavyweight computing was on the back end. This is called a two-tier architecture. Then we moved to a web or an N-tier, or really like a three-tier architecture, where you had the interface, the business logic, and the data were all separated. And what we're headed for, not there yet, headed for, is something that's platform neutral. This is where the cloud really comes in. When we talk about cloud computing, it's heading towards something being platform neutral, where you can get access to these systems via your Android phone or your iPad or your laptop or whatever you happen to have. And notice all the way on the right, the programming languages for each of these generations are different. The skill sets are different, and yet every single one of these exists today. So a quick trick for how to avoid legacy systems is to layer, to separate things apart. And this is what we saw when we moved towards N-tier architectures, where N-tier essentially says that on the very bottom you see you've got your data. At the very top you've got your interface, which might be a web browser. It might be a customized app that's meant to be an interface. You think about a lot of iPad apps that you run today. There's no smarts inside of the app. It's a native app on your iPad that's hooking to data and computing on the back end. That's actually doing all the work. So that's another example of separating off the interface. And then what you've got is the business smarts, the process, the domain, all those sorts of things are the layers in between. So you partition this apart. Well, why does this help you to avoid a legacy system? It avoids a legacy system because I can change independent parts without changing the other parts. Remember, we talked about this, that the budgets are way too big in maintaining these things, so you're never going to get budget to displace the entire thing at one time. However, if someone said, you know what, I got this one database over here, I think I can put that one to sleep and move that over to a modern database. Here's some budget. Not just enough budget to do that this year. That's the only thing you're going to do. Your user will never know the difference. They're doing everything exactly the same. But what they don't realize is they switched off some completely antiquated database onto something modern. Okay, great. Step in the right direction. Next year, we're going to pull the module that we were using for authentication. We're going to throw that one away. We're going to replace that one. These are the sorts of budget levels that you can maybe afford. And you might think of it this way. We think about what changes the fastest. You've got data, process application, and interface. There's your three tiers. Data stays around forever. I mean, we have data that's been around for 20, 30, 40, 50 years. And that's fine. The cost of disk space has gotten so cheap that there's no reason not to keep it forever. That's fine. Not hurting anybody. But what I don't want is I don't want it coupled to business processes, which change more often, and I certainly don't want it tied to the interface, which is going to change all the time. So I have to be able to decouple these. All right? So that's the key. Whatever you do when you architect, and that's why architecture is important, is because that's an architectural issue is decoupling these three layers. This little four-quadrant chart here just kind of gives you a snapshot of how to think about a legacy system and whether it's a candidate for modernization or not. If something has high business value and fairly low technical quality, meaning that it's really important and it's really not doing what you need it to do anymore, that's a good modernization candidate. That's the green square in the lower right. Then on the other extreme, if something has low business value but is reasonable quality, just keep maintaining it. Just keep maintaining it. It's probably okay the way it is. If it has low business value and also low quality, think about replacing it with a commercial package, because it has low value to your business anyway, so you might not really care about that. But if it has high business value and high technical quality, then what you want to do is sort of some sort of low priority re-engineering, where you're slowly rolling these parts out. You're identifying components that have obsolesced and are replacing those, but routinely. You're not letting 5 years pass. You're doing it routinely. Some other things that you might think about that get you there are the level of intrusiveness with upgrading something. So if you have to shut something all the way down, that's extremely intrusive. If you can do it in a way that your users can't even tell the difference, that's pretty good. Some non-intrusive things that we've seen are screen scraping and legacy wrapping. Screen scraping is where you've got a system that you might not even know how it works, but it produces it puts pixels and text and what have you up on a screen for you as your interface. So you scrape the screen. So when you put a query into a database, you have no idea what the format is of that data coming back. But I know exactly what field on this screen it puts the answer. So I'm going to scrape the answer off of this, and that's how I'm going to interface with this database. Actually, use the interface, the screen itself, as the conduit between what I'm going to move off of from what it is now. It can be very problematic, and it's also very fragile, so you don't want to do it very long. The other thing is legacy wrapping, where you can do maybe something as simple as XML wrapping of old systems, so that they appear to speak XML on your system, but they're really not XML at all. I'm not going to dwell too much on this slide. We've said most of this already, but just some formal definitions of architecture, and these are from IEEE documents. Again, talk about the structure of the components and their relationships. Also look at the bottom. We're going to talk just a couple slides here next about something called DODAF, D-O-D-A-F, the DoD Architecture Framework, which is a way of thinking about it. It's a more formal way of thinking about this, and in a lot of cases it's going to be overkill. But the nice thing about DODAF for what you're going to be doing, with the sorts of things you might be involved in, is you can kind of pick and choose which pieces of it that make sense for your application. So I kind of like DODAF for that reason. It's very scalable. You can do just one part of it and benefit from that. You don't have to buy into the entire thing. But architecture equals the structure of components plus their relationships plus the principles and guidelines by which those relationships and structures are going to work. And what you're going to see in the next couple slides when we look at what DODAF actually is, I'm going to put a whole bunch of documentation on DODAF on our website for you to look at if you're interested in more detail. There's a lot written on this, whole books written on it. It's extremely robust, but it's supposed to be a way that if you really buy into it, that you can so thoroughly specify a system and all these different quote-unquote views there, because different people are coming at it from different angles. But you look at these different views that give you a different perspective on how the pieces are going to work together. You should be able to really understand what each module is supposed to do, how they're going to work together, any side effects that might occur because of the interaction between these different modules, and it really should help to avoid legacy systems, because it's going to help you to tear things into parts and implement them independently. Now these are all the different architecture views in DODAF, and as I said before, very commonly we don't see all of them. The major programs probably will use all of them, but we do things broken into operational views and system views. So we're going to look at those in a little bit more detail here in a moment. So if you think about the last slide and what these different OV and SVs actually are, they're different slices of this architecture. So if you think from the very top, you've got operational activities. Well, there's an operational view of those activities, and there's a formal way of documenting exactly what you mean by that. And they produce information elements. Well, there's an operational view that does that. And then those are fulfilled by data exchanges. Well, there's a system view that describes exactly what those data exchanges might be. And then those read and update the system functions. Well, there's a system view that describes that. So it's cut into these different slices, and taken as a whole, it thoroughly describes everything the system is supposed to do and how it all works together. You should understand that a big motivation for DODAF in the first place was to deal with what they call the acquisition triumvirate. You learned a little bit about this when we talked about JSIDS itself. We had a slide very similar to this. But a big problem in DoD acquisition is that the folks who are specifying the need, the folks who have the resource allocation, and the folks who actually have to develop it are not the same folks. So having a language by which they can speak to one another from their own perspective, so that they understand what each other is doing, was absolutely essential. And DODAF is meant to fill that role. So DODAF allows each of these to talk to each other in a common language using the same terms so that we're not misunderstanding. You're calling it that, I'm calling it this. We want the material developer to understand exactly what is required, and the buyer needs to know what he or she is buying. The next step would be to think about getting to a service-oriented architecture, and this is heading towards the cloud. The service-oriented architectures, or SOA, were a precursor to what you're currently hearing called the cloud. So one of the questions you want to ask is, how much does it cost to wrap an existing system to turn it into services? Remember, we talked about wrapping things with XML. SOA is a way of doing that. Can a new service be developed cheaper than just wrapping the old one? How much infrastructure is actually needed? Do you need new hardware, new software? And how are you actually going to invest in the infrastructure for doing this sort of thing? So these are all questions that are coming up because service-oriented architectures are a very different way of doing what we need to do in defense-oriented systems. And when you think about simulation is a little bit different animal. We've just begun to think about service-oriented architectures for simulation. We're going to talk about that in more detail a little later. But the same scenarios can be applied to simulation that could be applied to any other aspect. And just in case you're wondering, okay, so you're beating the drum for architecture. That sounds interesting. Maybe I buy into it. Maybe I don't. Well, it's important to know that the federal government, and most importantly, the Department of Defense, has bought into it. There is a mandate for architectures, and there is DoD policy on using architectures and the importance of these. This stuff wouldn't be there if they didn't think it was important. So what I'm saying is, I believe legitimate, that we really do need to be experts at architecture. And we already mentioned a little bit of this, but how is it used today? Architecture, that is, certainly in the JSIDS process. We talked about that. Planning, programming, budgeting, and execution, making our budgets, being able to plan out in the future, to pound for money for multiple years for some of these big systems. Having a thoroughly fleshed out architecture is critical to being able to do that. The whole defense acquisition system relies on this. Certainly portfolio management. Some of you who will end up as program managers and will be managing a portfolio, you're going to want to have some type of an architectural aspect of your system that other pieces are plugging into that's well understood. It's going to help you to understand where you're going and what it's going to cost to get there. And where we think we're headed in the future with architecture is certainly layer connectivity, no question about that. We're talking about modularizing functions and services. We're definitely heading towards distributed computing. We're going to talk in a little bit about service-oriented architectures and cloud computing and how that applies to simulation specifically now. We're going to be standardizing protocols and data standards. A lot of work in DoD modeling and simulation in data standard development as a communication mechanism, so that if I call a detonation this, you call it the exact same thing, so we don't misunderstand and we can interoperate. Interoperability is the driving force behind this, but system development, managing costs are all critical as well. So that gives you a really high-level snapshot of system architecture. I wanted to give you a few slides on DODAF in case you don't look at it any more deeply than this. At least you know what the acronym means and what it's meant to be. It's just a way of thinking about architecture. There are other ways. There was something called MODAF and other sorts of architectural frameworks, many of which you can see residue of each other of them in the newer versions. But a lot of people think about this stuff and how it's going to work, and think about system architecture as a critical component, not just something you very quickly slap together and then you right away start writing code. You want to think about this very carefully in your program. If you want to have a phase of your program that's very prototype based, that you specifically don't want to architect because you don't know what needs to go into it, that's fine. But be prepared to throw some things away. Consider it your prototype phase, and there's going to be some of it that you're just going to discard. But when you get into a full-blown program of record that you want to maintain over some number of years, you better be ready to architect.